So what we're going to look at is using what's called a left endpoint estimate to estimate the area underneath a curve. So this is kind of a hybrid of sort of theory, but also an example, and you'll see why that's the case in a moment. Um, so yeah, the question says this: using a left endpoint estimate with rectangles of width 1, determine the area under the curve of the function f of x between x equals 0 and x equals 6. So let's just point out what's going on here. We've got some function f of x. Actually, not interested in what the function is, but we just know it's some function f of x. And what we want to do is we want to use what's called a left endpoint estimate. So what that means is we're going to start putting in endpoints, or we're going to start putting in points at intervals of width 1, starting at 0, because x starts at 0 and goes to 6. So you'll see what I mean in a second. So here we're going to have 0, f of 0, then we're going to have 1, f of 1. And obviously, as we move along, these values will go to 2, f of 2, 3, f of 3, 4, f of 4, and 5, f of 5. I'm actually going to stop there, and you'll see why in a second. Because what we're going to do is we're going to create our rectangles between 0 to 1, and then 1 to 2, 2 to 3, 3 to 4, 4 to 5, and then 5, you'll see. So let's put those rectangles in. So that's our first rectangle there. And so you'll notice it's got a width of 1, as it says in the question, and it's got a height. I'll encourage you to think about it, but the height of this rectangle would be f of 0, because that's the function evaluated at 0. So that means that's the height of the function. That's why it's a left endpoint estimate, because we're taking the left endpoint of this function. Okay, and then we put the next rectangle in. Again, the height of our function now is is f of 1, because the height of the function is f of 1, and again, the width is 1. Okay, and then we keep drawing in our rectangles. And so the height of this rectangle, the left endpoint, is f of 2. The height of this rectangle 4 is f of 3, and then that one, and then finally our sixth rectangle. And so now the question is, what is the area in total? Well, we obviously know how to compute the area of a rectangle. It's just obviously length times width. So rectangle 1 has an area, hopefully you would agree, of 1 by f of 0. And then rectangle 2, again, has a width of 1, but has a height of f of 1. And then similarly, rectangle 3, 1 by f of 2, 4, 5, and finally rectangle 6 has that height. Okay, and so now what we need to do to find the total area is obviously add all those rectangles together. So the area, hopefully you'll recognize, is that there's a common factor of 1 in all of these. So if I was to add these all together, I could actually take out 1 as a common factor, because they all have the same width. So I could say 1 multiplied by f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5. Now, because we did a left endpoint estimate, we actually don't go all the way up to f of 6, and hopefully you can see why. We're going to this point here. We're only going to the x equaling 5. Okay, that's going to be the left endpoint of our final rectangle. And obviously we can simplify this last part here. So 1 times anything is just itself. So we can say, to answer this question, that the area underneath this function between 0 and 6 is f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5. And that's what we call doing a left endpoint estimate. And you can imagine if you knew the function, if you knew what the function was, it might be like, negative x squared or something like that. Obviously, these numbers would have values now. Okay, we just sort of did it generally to sort of get the theory across of what's going on with a left endpoint estimate. Later on, we'll connect it with the idea of integrals, because what you can start to think about is if you made those rectangles smaller and smaller and smaller. You might notice at the moment that this is an overestimation. Because our green function is a decreasing function between 0 and 6, using a left endpoint estimate, you can clearly see is going to overestimate the area. But you can imagine if I made these triangles have smaller and smaller width, that my error would get less and less. And so that's basically what the essence of integration is later on. You find the exact area under the curve by making the rectangles have a very, very, very small width. Okay, so hopefully that clarifies what a left endpoint estimate is.